Hello, welcome back to Networks and Cybersecurity. Today we're going to continue with crypto, and then we're going to move on to some transport layer security goodness, TLS, time permitting. But first, let's start with, I don't have slides for this, but a little bit of tech news today. Yesterday, for an hour or two, all the Macs in the world stopped working for a little while. Or at least they stopped working well. You could open Apple official apps, but there was a significant delay in opening some of those as well. And the reason is bad network programming. That's right. The reason that you can't open applications on your local computer is bad network programming. So let's talk about why. What does Apple do? First of all, many will argue, including me, that when you buy an Apple computer, you don't own it, you only rent it, because you're not allowed to do what you want with it. There's a very specific amount of limitations on what you can do with Apple products. And one of those limitations is what you are allowed to run. And so Apple makes sure that you're running what you're supposed to run by checking with a certificate authority every time you run your application. And it sends the certificate authority a bit of information, your computer, your IP address, a hash of the program that you're trying to run. They have a hashing process, as we've been talking about here, so that you can hash the source code of an entire program. That way you can identify that a program is unique, because remember, hashes are unique. And then checks to see if their certificate's expired. It also probably sends things like your IP address and stuff. If it doesn't hear an answer back, you can't run the application. Now when you're offline, weirdly, it just assumes that everybody's good to go. So if you just turned off the Wi-Fi module on your Mac or just disconnected it from the network, you probably would have been able to use it again. But while it is online, and this is where the network programming mistake came in, it interpreted a delayed or non-response as the application being unable to run instead of as a failure to connect to the application server. So what Apple should have done was at least made it so that if they couldn't reach their little verification server, that it wouldn't fail to launch your application, or that if it timed out, let's say give it 5 or 10 seconds to attempt to connect, and if it couldn't connect, then default to allowing the user to do what they want. There's actually a little add-on app for Macs called, I think, Little Snitch, that lets you bypass Apple's control of this entirely by redirecting all of those requests to your own machine, and then you always just answer in the affirmative, and then you can run whatever you want to run. But in the newest version of macOS, they made that not work either. So it's kind of ironic that they got rid of this plugin or app or whatever it is as soon as they had this problem where there's basically a global outage. So very funny for Apple. Still a lot of reasons that Macs are good. Still a lot of reasons why people prefer them to Windows, but definitely not a computer that you fully own. More of a kind of a partial sort of rent or some kind of sharecropping-esque arrangement with Apple computers, and also some weird network programming there. So if you rely on a service that needs to be up in order for your service to function, and it's very business critical, as is the Mac operations of users worldwide, make sure that it's highly redundant, and make sure you have a plan for when it goes down, because there's no such thing as perfect uptime. The best anybody can give you is 4, maybe 5 nines. That's up 99.99 or 99.999% of the time. You'll notice 99.999 is still 1 day every 3 years. One 1,000th down, right? So 1 day every 3 years when nobody can use your service. That's not great. Who knows if Apple will lose any money over this? I imagine someone will probably take them for some cash as a result. Alright, so let's move on to asymmetric encryption, where we left off. we'll just start from the beginning because we weren't too far along with it anyway. Alright. So in asymmetric encryption, the key that is used to decrypt is different from the key that is used to encrypt. Remember that. So the key that you use to lock the door is different from the key that you use to unlock it. This usually means you have some kind of mechanism with two locks, and that is basically what we have here. We have some kind of mechanism with two locks, or two locking and unlocking mechanisms, where one is able to only lock and one is able to unlock as well. You see some very elaborate locks, single locks like this actually in the real world. You've probably never encountered one because they're so rare. But you can look them up online. There are locks where there's like a shorter variant of the key that can be used to lock it, a longer variant of the key that can be used to unlock it. That's kind of an analog, but a better analog is the mailbox example I'll give later. So when you're sending your public and private keys along, you can send the public key to anybody you like, because the public key is only used to encrypt information that is intended for you. So if the public key is the one that can only lock your house, you can hand that key out to anybody, because you don't care who's able to lock your house, unless your house being locked is a problem for some reason. So you give everybody you like the public key, since that only lets them lock, or in this case encrypt, your resource. The private key you must never give to anybody, because the private key is what allows you to read the incoming messages or to unlock your house, broadly speaking. There are other applications where public and private key cryptography are used, but this is the one commonality. You always keep the private key safe and you never give it to anybody. If the private keys of your server are compromised, or if your personal private key is compromised, that's very bad news for you in pretty much any context. Okay, so the analogy that I gave is this mailbox analogy, where the public key is the slot that anybody can put mail into. The private key is the only key that's able to unlock the box and actually extract the messages from it. So there's a public slot available where anyone can put their messages, and then there's a private key that is used to actually decrypt or read them. There are a few examples, but the most popular today, or at least the fastest growing, is elliptic curve, which you can learn more about here at John Carroll in the cryptography class in mathematics. Elliptic curve is some really amazing voodoo, and it is the reason that I think cybersecurity classes no longer teach, or should no longer teach, how encryption works mathematically. We're going to take a weak crack at it. But I'm not going to ask you on a quiz or go into too much detail, because the math behind crypto has become, let's say, too complicated for an undergraduate course, and I don't think it's worth diving into anymore. But I will point it out when we get further along. And then you've got your RSA, your DSA, and the original Diffie Hellman. So Diffie Hellman is named after the inventors of the first public key exchange. And there were actually three of them that invented the algorithm. There was Merkle too, but Diffie Hellman Merkle was a mouthful, so they just sort of omitted Merkle's name. That's a shame. That goes to show you that if you're going to be an academic, make sure that your last name comes early on in the alphabet. Otherwise you'll be forgotten in history. Poor Merkle. Diffie-Hellman allows two parties to exchange secure messages when they know the channel is insecure. And that's technically symmetric, because you end up with the same key on both ends. But we call this the first asymmetric algorithm because it allows these two parties to have a shared secret on their end. That's what we consider the private element to be, and still exchange info over a insecure channel like the internet. So let's consider how you would do this. And again, this is really generalized to just math functions instead of the specifics, because again, the math itself, the functions, have grown to the point where they're so complicated that it's not really even worth trying to look at them. It would take a few weeks just to get into them, and we don't have that kind of time. So first, consider that there is a math function. We don't know what it is, but we'll call it g, and you give it a value n, and it's irreversible. So it's like a hash function, but not quite, and it's very hard to evaluate, and that it's very hard to get n back. And let's say Alice wants to talk to Bob, She has her secret x, Bob has secret y. They both do this function, this very difficult irreversible function, and they end up with g of x and g of y. They exchange those things over the insecure public channel. So since that function is hard to reverse, or almost impossible to reverse, even if somebody snoops your message over the channel, they're not going to be able to extract your secret, your x or your y. Then both parties compute their shared key, and they do that by applying their hidden value, their x or their y, to the function that they got in the exchange. So they do g of x to the y or g of y to the x. Then the hint here is that this key, because of how this math works, ends up the same. So the outcome of g of x of y and g of y of x is the same. So they compute the same shared key. At the same time, anybody that intercepts g of x or g of y along the way isn't able to do this because they don't have either x or y. So as long as both parties keep their private x and y keys safe, nobody else can compute the shared secret, and they can encrypt things using that shared secret without having to worry about it. That's the basics of it. So here's how that might look if the function was paint. Simple colored paint. If you're colorblind, my bad. You're not going to get this slide at all. So let's say that they have a paint in common. This is their function. It's the yellow paint. So that G function is to add yellow paint. Now, adding yellow paint to something is an irreversible process. You can never unyellow it, and you cannot easily extract the original color. In some ways, this is a bad example because you can extract the original color if you analyze it sufficiently and you remove the yellow pigment. Yes, you could figure out what the original color was, but for the sake of argument, you can't physically split them, so let's assume you could never recover the secret color. Alice's secret color is orange and Bob's is cyan, and when they add yellow, they get completely different results, and they send those to one another. So Bob sends Alice his bluish, cyanish paint, and Alice sends her lightish, orangish paint over to Bob. Now they both have each other's combined paint, their G of X and G of Y, but neither of them have the original secrets from the other person. Next, they combine their own secret to the paint that they got, and you should note that in this case, because of how it was done, Alice added orange, her secret, Bob added cyan, his secret, then they exchanged. Now Alice adds orange, her secret, Bob adds cyan, his secret. They have done the same steps at this point, so they will produce the same finished result, that ugly vomit brown, that is the secret color at the end. So they will produce the same common secret. And that's essentially how this private key exchange is supposed to work, that you result in the same common secret at the end of Diffie-Hellman. Okay. The original Diffie-Hellman is still common today. There are still applications that use the original Diffie-Hellman, which is interesting if you think about it, because cybersecurity standards usually advance so quickly. But because Diffie-Hellman has that math function that is kind of ambiguous, you are able to specify new math functions as the old ones become compromised for different reasons. That leads us today to use elliptic curve cryptography, which is the current modern standard. The previous standard was to use a modulus system, and it's still used, it's probably still the dominant system because it hasn't quite become obsolete yet, but it's still considered less secure and is starting to become obsolete. Now, the basics of elliptic curve cryptography in a nutshell are that instead of picking two colors, you both pick a very fancy mathematical function, and then your secret is basically 2 points on the curve for that function. And that's about as far as I'm willing to go into it. So a couple of Diffie-Hellman based algorithms, IE Gamma, IES, these are different application examples. Diffie-Hellman's broken down today into groups. So you've got your groups 1, 2, and 5, which still use the modulus system. Anything above that line considered outdated. Group 14, really outdated too at this point, but acceptable at this point because we need to have an acceptable modulus version for a bunch of the legacy applications that aren't configured to run on elliptic curve. There's also the problem of performance of elliptic curve. Modern machines run elliptic curve very well. Older machines sometimes not so well, and so for the majority of the world, which still runs on older machines, there needs to be an acceptable Diffie-Hellman modulus group that they can do, because a lot of machines were built with the idea of calculating those modulus type mathematical formulas quickly in mind, not with calculating elliptic curves in mind. So you'll notice what changes between the different groups is the number of bits in the keys. So we just keep making the keys larger and larger. This is a performance trade-off. The larger it is, the longer it takes to encrypt and decrypt, more or less, but then the more security we have, because the longer it takes to encrypt or decrypt, the more times the attacker has to try in order to crack the key. Now, 2048 modulus is essentially unbreakable on any modern machine. Even if you had a giant array of supercomputers, you wouldn't be able to break it. But as quantum computing catches up in the mainstream, many people suspect that intelligence agencies are already quantum computing and they can hack keys below a certain point because they're already able to do so with their fancy quantum computing algorithms that can do it much quicker. But that's not confirmed. No one knows that for certain. But it might be the case. Who knows? Elliptic curve, a little bit more resilient to those kinds of things. So let's say when you would use Diffie-Hellman or something like this. One common place is in VPN connections, which you should be familiar with because you connect to your virtual machine often for different assignments in this class. So when you're connecting to the virtual machine, the client connects first to the remote server that hosts it, and then the client and the server have to agree on which Diffie-Hellman group that they want to use. So they actually will exchange information about which ones they both have available before they establish the secure session, and then they will choose the strongest one that they both support. That means that anybody who overhears the conversation, so anyone snooping along the way, actually knows exactly what method you're using to encrypt and decrypt your traffic, which is even more of a testament to how great these algorithms are, that even an attacker that knows exactly how you're doing it, you can go and look it up in a book or in a reference, there's no mystery to it, they still aren't able to compromise your stuff. And then the clients and servers generate their private keys, x and y, like we said before. They exchange that g of x and g of y, compute the g of x of y, and the g of y of x, which should be the same thing. And then the connection is established and your VM traffic is encrypted from there on. That should be how it works for most VPN connections. All right, so any questions on symmetric or asymmetric crypto before we move on to another example of the use of cryptography? All right. Now, I don't think we're actually going to get to SSL and TLS because of our different server issues and because of how annoying it is, but we might. So I'm going to give it a shot. I'll at least go through how it works. And you don't have to memorize all the steps or anything. So the fact that I have all the steps over there is not to dissuade you from learning it. I just want to introduce this, as it is probably one of the most important ways that traffic is encrypted over the internet. Even if we don't get to use it in this class, it's something that you ought to know for your applications in the future, because if you're building something for real use, for enterprise use, this is probably how you're going to end up doing it. Okay, so your transport layer security, TLS, was once known as the Secure Sockets Layer, SSL. They changed the name after making some significant improvements. They wanted to basically wash off the shame of SSL, and so they have gotten rid of the name. But a lot of people still call it SSL instead of TLS, just for historical reasons. So if you run into anybody who's a little older, they probably still call it SSL. SSL, though, spans from basically the early 90s up to 99, and there are probably still some services out there that use SSL 3.0, even though they really shouldn't, because it's very insecure. TLS 1.0 starts off where SSL leaves off, so TLS 1 is actually SSL 3.1 if we had kept counting, and the current latest version of TLS that's actually deployed is 1.3, although 1.4 is It's coming out as well here. And that's about it for the versioning. The goal of TLS or SSL, I'm just going to use those interchangeably here, but I'll try to stick to TLS whenever I talk about it, is to add a guarantee of security on top of TCP. So we've got a lot of things at the transport layer. We've got the guarantee of eventual arrival. We've got the guarantee of arriving in order. We've got the checksumming and everything, so guarantee against corruption on a few different layers. We've checksummed at least 3 times. So you have a few different guarantees by the time we get up to TCP, but none of those were designed with security in mind. They were all built in the 70s and 80s, and they just assumed everyone would be honest all the time and they wouldn't need security. And also they weren't able to take on the overhead that security would give them because their machines were pretty low power. So TLS was designed to add a guarantee of secure communication on top of TCP because all internet traffic passes through public channels, public routers, that sort of thing, and we don't want other people to be able to read our data along the way. Now, why did they choose TCP instead of UDP? Well, because TCP already gives you more guarantees, such as reliability, and UDP is supposed to be the sort of low baggage one that anybody can build on top of. So TCP was chosen as the one that would get the security layer over it. So is TLS Transport or application layer, which is the next layer up, which we haven't looked into besides this? If you get asked this question on a test, generally speaking, the answer is transport layer, but some people call it its own layer. So TLS does run over TCP, but it is basically just adding more headers to TCP. In addition to some protocol differences, it has a much more elaborate handshake. It basically just adds some headers and then sends the same payload. And then once the traffic is encrypted, it doesn't look all that different from regular TCP traffic. If you look at it from the perspective of a developer or an operating systems developer or whatever, TLS looks a lot more like transport layer than anything else. So for example, if you were to make a TLS socket in Java, it looks pretty much exactly the same way the making of a TCP socket looks. There's a little bit of a different syntax, but it's very similar. You have to use a factory instead. We'll get into why you have to use a factory a little later, but otherwise it's the same thing. You create the factory in this case, which you don't need to make for TCP obviously, and then you just say SSL socket equals, and then you ask the factory to make a socket for you, specify the destination, and specify the port. So it looks like transport layer from the Java point of view. Now you'll notice that Java still calls it an SSL socket too, which is a little bit annoying, but since again Java's a fairly old language, they didn't want to change the name. If you change the name, then everybody's old code stops working, so it was easier to just keep it as SSL socket since everyone ought to know what you're talking about anyway. So since TLS clearly runs on top of TCP, some people argue that it's application layer because it does add more, but since it really just extends TCP, some people argue that it's transport layer or call it somewhere in between. And if you look in something like Wireshark, it will call it the secure sockets layer, so it'll actually give it its own layer. And I guess this is probably the more dominant way of thinking about it, since that's the way Wireshark does it, and Wireshark is the dominant packet inspection application, so I guess we'll just defer to what Wireshark says about this and say it's its own layer, the secure sockets layer, which again is annoying because it's no longer called secure sockets, but is what it is. Okay, so to establish a secure channel, we need a shared secret. And again, the method we use this is a cipher. How do you communicate with a stranger over the internet when you are also communicating over a public channel? If you transmit the secret, everyone else sees it too. How do you generate a secret without transmitting it? And now, let's go through some steps. So before we start, notice that if you do this in Wireshark, so if you observe the TLS handshake in Wireshark, you will see that a lot of these are combined into a single segment. So you'll see multiple steps in one segment, and Wireshark will label them. It'll give them different drop-downs. All of these have either the same or very similar names in Wireshark, But again, if you want to observe this, you'll notice that a lot of these get combined into a single segment. And here I'm going to use this wonderful visual guide that I'll link somewhere after this, where you can see a illustrated version of the TLS connection. So we're going to start with the client hello. This session begins with the client saying hello. Alright, so 1.3 adoption is slow. I'm going to refer back and forth here, so it might be a little bit confusing. 1.3 support is still kind of slow to adopt, but almost everybody supports at least 1.2. At this point, the client sends the server a pseudo-random number. This number is only used one time, so we typically call a pseudo-random number that's used once a nonce. This is going to be used later to generate a shared secret. And duplicate random numbers within the same time frame, from the server's point of view, usually going to be denied to stop you from being able to steal somebody's existing session. If there is one, we're going to send the session ID. If the server supports it, you can sometimes just send the session ID to resume a session that you've already had previously and not have to go through the rest of the handshake. And then, as I mentioned, for Diffie Hellman, you have to exchange your different ciphers that you're available to use. So in the client hello message, the client sends the list of ciphers that it supports. And you can also, although this is sort of obsolete and very seldom used, send a list of supported compression methods if you want to, as we did for our previous homework, compress everything in transit. So TLS actually gives you the ability to compress your information directly without having to deal with it on the application development side. So this is actually a very convenient way to compress your byte arrays without having to do anything on your end except provide the TLS support, because you don't have to provide these compression methods manually. Unfortunately, most servers don't support the compression thing anymore. The overhead isn't worth it, so generally you still have to do your compression manually. And then there's a bunch of other optional information here. They call it extensions here, but we won't go into that. Alright, next we get to the server hello. The server in this case says hello back. It again tells you what protocols it supports, so which versions of TLS it supports. Again, it'll send you a pseudo-random number, so this is going back to the client. It's a different pseudo-random number. Again, it's going to only be used once, so we call that a nonce. It sends the session ID that we're going to use for the rest of the session. Now, this will either be based on the client session ID, so the one that they just sent, which is the server basically agreeing to it, or it will generate a new one if it wants to use a new session ID, or it'll send empty, and an empty session ID usually conveys that this server does not allow sessions to be restored once they are terminated. So these sessions are all one-time sessions. As soon as you end the TCP connection, so you do the finish handshake and you disconnect, you have to start this whole process over again to make a new TLS connection. Just like the client, it will send its list of ciphers, only because the server already knows which ciphers it's got, it will just look through its list internally and pick the strongest one that's also in the client's list and just send that one. So it won't send the whole list to the client. There's no need to send the whole thing. It'll just send the one that you are going to use from that point on, so the strongest one that you both support. And likewise for the compression, if it was requested, if the server supports it. Again, both fairly rare. And again, some extras. All right. So, before we get into the certificate, we're going to go on a little bit of a side note. And this is the reason that all of the Macs in the world went down for a bit the other day, the certificate. So TLS and most other public and private key exchange algorithms rely on something called trust through authority, which is basically that there are organizations at known places in the world that are granted the authority to issue what we call certificates, and we call those organizations certificate authorities. And a certificate authority is responsible for basically validating that a particular IP address, so a particular server, owns a particular public key. Without this validation step, you would be able to complete the handshake in terms of setting up the encryption key and in terms of creating the shared secret. But that would be pointless if you didn't have some guarantee that the server that you were talking to was who they say they were. So whenever you want to host a server on the internet, you have to register yourself through one of these certificate authorities. And that, generally speaking, costs money. We'll go into the money in a little bit. But the certificate authority will basically issue you, through different cryptographic tricks, let's call it a file, that tells you that your IP address, your server, owns the public key that you've shown them. And you can show this to anybody that connects to you so that they can be confident that you do indeed own that public key. And if they're not sure, they can go back and they can ask the certificate authority, is this certificate legit? And the certificate authority will answer you. So that is the service that went down for Apple yesterday. It was the service that clients can go to present their certificate that they have stored for a particular application and ask, is this legit? And Apple should respond, yes, it is. The reason that Macs have to do this every time they launch the application is to make sure that the certificate hasn't been revoked yet. So although certificates can be issued, they're usually issued for some time, and then they can also be revoked in case something goes wrong with your app. Apple decides it shouldn't be available for Mac anymore, whatever, they can revoke that certificate at any time. So the reason that Macs check every single time an application launches instead of just when the certificate expires is on the off chance that the certificate was revoked. So it's actually a lot of overhead for very little reason because certificates are quite rarely revoked. The only reason your certificate might be revoked if you're a Mac developer is if your app is suddenly found to have malware or it doesn't comply with some other rule that Apple has made. That's relatively rare. So this check is kind of unnecessary. But that's basically the source of the failure, that they have a check every time to make sure that the certificate is still valid. Now, because certificate authorities, there aren't that many of them around the world, and this would be a ton of traffic to them if they were able, if they had to check the certificates for everybody all around the world all the time, because there are millions and millions of TLS sessions created every second around the world. The certificate authorities designate some of their authority to other entities called validation authorities. And these authorities can't issue certificates, but they can validate that a certificate is legitimate. So this complicates things a little bit further. You connect to the closest validation authority. How do you know which certificate authorities your computer trusts? Well, these are going to actually be built into your operating system or into your browser. So whenever Windows updates, it updates its list of certificate authorities that it trusts. Whenever Chrome or Firefox or an Explorer update, they update their list of certificate authorities that they trust. One interesting technique that has persisted is that servers can staple basically this file to their certificate message. We call this the OSCP staple. And that confirms that the validation authority agrees that your certificate is legit. And again, through different cryptographic wizardry that we're not going to go into, this is actually a valid system. Even though the server is sending you basically, hey, look, I have this coupon that says I'm legitimate, because you have these trusted certificate authorities stored on your system, and because of the way this staple works, you can actually validate that a server is who they say they are without speaking to any validation authorities directly. But you will still sometimes see connections go out to validation authorities to check a certificate, either because the staple is lacking, as a double check, various reasons. Alright, so on to, I said we would go back to the cost thing. So the generation of a certificate used to cost not a lot of money, but some. It cost more back in the day. It was maybe like $10. Now it's down to, depending on where you go, you can get it for single-digit dollar costs. As recently as a few years ago, until a new service comes to the market called Let's Encrypt. And Let's Encrypt is revolutionary because it is free. And so finally, everybody can make certificates for free. This was a big deal, and they start a few years ago. But whenever you're a new certificate authority, You don't have any trust. You're not on anybody's operating system. You're not in anybody's browser. And there's no particular reason for anybody to trust you. So every time a new certificate authority comes to market, unless they have huge clout like Google, so Google makes its own certificate authority, and it just puts itself in Chrome, and everybody has to deal with it because if you reject Google certificates, no one's going to be happy with you. A big part of the internet's going to stop working for that user. But Let's Encrypt didn't have that kind of clout, so what they did was they inherited somebody else's certificate. I think DigiCert vouched for them. And DigiCert basically signed their certificate as well. So they said, okay, things that Let's Encrypt signs are legit. When Let's Encrypt got bigger, which was very recently, about a month ago, they decided we have finally grown large enough and trustworthy enough that we no longer need somebody else to vouch for us. And now we are our own certificate authority. So this is how certificate authorities are born, grow, and then come up on their own. They come up, someone vouches for them, they issue a bunch of certificates that aren't bad, and then eventually they can go off on their own since they've earned everybody's trust. That means that if your device is older than Let's Encrypt and you haven't updated it, pretty soon a lot of the internet is going to stop working for you because a lot of the internet is now signed by Let's Encrypt. So this is the case for Android devices made before like 2016-ish, somewhere around there. So if you have an Android device before 2016 and it's no longer able to update, the built-in browser will simply stop connecting to services that use Let's Encrypt certificates, or it'll warn you that they're insecure. So that's something that's bad if you have an older Android. Someone asked, didn't they do that to Fortnite? So Apple revoked Fortnite's developer certificate, I think, briefly, but then they restored it. I don't know about the drama with Fortnite completely, but yeah, there was some revocation of Epic Games certificate at some point. Alright, now that we've covered certificates a little, generally we call these certificates X509 certificates. That's the most common kind. Our next message from the server back to the client is the server certificate. This is where the server presents their public key, and if they have one, they present their OCP staple in the next message in order to confirm that they are the rightful owner of the public key. But in this step, they send their host name, so their IP address, and then what it's known as, so if it's known as google.com or cats.com or what have you, they send that too. And then they send their OSCP staple if they have it. Otherwise, you have to connect to a validation authority to prove they're legit. So this is your proof from a trusted third party that the owner of the host name holds the private key for this public key, so that you are who you say they are. Alright, server key generation is our next step, but we skipped a couple optionals in the visual here. Clients can ask the server to send this message, the certificate status, when they send the server hello. This is one of the options that they can present themselves. If the client sends this message that says that they're willing to accept an OSCP staple and they're not going to talk to the validation authority themselves. So if the server gets this message, then in the previous step it will just send an OCSP staple. If not, then the client will talk to the validation authority themselves after the server presents their certificate and make sure that the certificate is legit. But next, we go to server key exchange. Many modern ciphers require the server and the client to exchange some extra information before they can establish their encryption, so that is done in this message. In message 2, we agreed to the cipher. The server sent the which cipher we're using message out. Some ciphers don't require this message, but most of the modern ones do. And the reason that this is required is outside of scope, but if you want to, you can follow along with it in the image version here. The calculation of the curve and everything, this is a simplified example, but they've basically picked a random number and done some stuff on the curve and whatnot. If it's interesting to you, again, I'll link this at the end. Then the keys are exchanged, the server exchanges the key. This is part of the same message as the key exchange generation. I just lumped these together, the key exchange and the key exchange generation. And then the server sends a hello done. So I'm done, your turn. And this is, again, typically combined into one TCP segment. So you'll often see all 1, 2, 3, 4, 5 of these steps combined into a single segment, or sometimes two. So you'll see the hello and the certificate as one segment, and then the key exchange with the done as another. Now it's the client's turn to talk again. The client does their key exchange generation. Again, the way they do it, kind of out of scope, but they will encrypt a random number, another random number, not the one that you saw earlier. So they'll encrypt another random number. This is now known as the pre-master secret. And they'll encrypt this with the server's public key. So if they send it out over the public internet, they can still be confident that the only group that's able to read it is going to be the server, because only the server has the private key to decrypt it and extract this random number. And it sends this over to the server. So again, the public key used for encryption, and messages encrypted with the public key can only be decrypted with the private key. Server will decrypt this message and extract that shared secret. And again, server can never share the private key with anyone, otherwise this whole thing is bunk. After you've got the client key exchange and the client key calculation done, which I've combined again all into one step here because a lot of that stuff is out of scope, but if it's interesting to you, please look at the visual guide. You see some lovely complicated stuff here. After all of that is done, we get to the change cipher spec. So at this point, using that pre-master secret and the cipher of choice, the cipher of choice is basically fed the pre-master secret in order to compute what is going to be the master secret, where all future messages will be encrypted. So this is similar to Diffie Hellman. At this point, we've gotten g of x and g of y on both sides, you could think, and now we're doing g of x of y and g of y of x. Not exactly the same, but it's very similar. And once we've computed the master secret on both ends, we both have the pre-master secret on the server and the client end, so we both do the same thing with our cipher to compute the master secret, and then we do not transmit it. Anybody that is snooping and manages to intercept the pre-master secret will still be able to decrypt all of our traffic, because they will also be able to compute the master secret. So it's important that we keep the pre-master secret safe as well. But the master secret will be used to encrypt everything going forward. The client sends this change cipher spec message in order to indicate that all the future traffic will be encrypted. Then it sends its handshake finished message in order to demonstrate that no one in the process came in the middle and tampered with it. So in order to show that all of the steps came from the original client, the client will take a hash of all of the previous messages that were sent and then encrypt it and send that. The server will decrypt that message, compare the hash against all the messages that it got from the client, and make sure that it's the same. Since this message is already encrypted in Wireshark, you won't be able to see its contents, and it will just come up as encrypted handshake or encrypted TLS message. And again, usually these are all bundled into one segment. Generally, again, the key exchanges are one, and then the change cipher spec and the handshake finished are one. Okay, now we get the session ticket, the change cipher, and the server finished. The server confirms that the change cipher spec has been issued, so it's ready to start communicating on an encrypted channel. It sends its own finished message, aka its encrypted handshake. Some servers at this point will also send their session ticket, which the client can present next time they connect to the server to resume their session without going through all these steps, if that functionality is available. Usually there's a limited amount of time for a session ticket, so you can restore the session, but it has to be within an hour or something. In some implementations, the client can present this to quickly resume their session during the hello phase, and other implementations will use the session ID instead. So this is actually, in addition to session ID, another way that some TLS implementations will allow you to resume sessions. Now from this point forward, in Wireshark, if you try to look at TLS traffic, it will just call it application data, and all the payloads obviously will be unreadable because they are encrypted. Okay, so why do programmers hate security? Why do developers like you hate having to implement security? It's because TLS is awful. It's truly, truly awful. We just went through, and even on the visual guide, there's like 45 steps that need to happen, right? It's like, whoa, it takes a while to scroll through this. It's really, really bad. And it is. And another problem is that, remember, we started with that whole list of ciphers you want to send over? Well, now you have to make sure that you're using up-to-date ciphers all the time in your application. That's awful. How do you even get ciphers into your Java application? Hmm. Once your ciphers go out of date, services might just stop accepting them, or your application has errors now, or it just stops working in other ways. TLS requires you to constantly update your application. So if you wrote an application that was perfectly secure a year ago, it might already not work and you have to update it again. That's why SSL 3.0 was in use 10 years after it should have been discontinued, because programmers are very lazy in the sense that they hate code that breaks itself and has a constant maintenance burden. This is the equivalent of having to put gas in your program every 5 miles. It's way too frequent of a maintenance cycle trying to get your security to run. TLS requires you, when you do it in Java at least, and well, when you do it in any language, it requires you to manually pick the ciphers that you are able to support, which means you need to make sure that they're on that machine somehow. You've got to manually pick the version that you want to use. You've got to invoke all these different libraries in order to get it to work, because you need your certificate library, your TLS library, your library for the cipher. All these different things need to be invoked, and there's a ton of other minutiae in setting it up. Altogether, establishing a TLS session in Java is something like 25 lines of code minimum, unless you get onto some really extreme shortening. It is very, very annoying. Nobody wants to stay up to date. And what's the latest version of all these protocols? What's the latest cipher? That is kind of outside of your scope as a developer. And companies don't want to hire somebody who's full-time Javanist to stay up to date on this, because those people typically command a high salary. A lot of organizations default to the easy solution, which is just to ask the system what cipher specs it supports and use the system default. But this is just shifting the burden, because now the user's IT department becomes the organization in charge of deciding what cipher you have. And it's very frustrating to your clients if the application you wrote doesn't work on their machine because you wrote in that it uses the computer's ciphers and it's their computer that's configured poorly, right? So if it's still on them, but it's your application that's not working, it's not much of a benefit to blame the user in that case. They're still going to be mad at you because your application that doesn't work. So if you're going to use TLS, which I hope that we'll get a chance to before the end of the semester, be ready to be very frustrated with it. It really is like pulling teeth compared to TCP. And UDP, you'll have to spend a lot of time consulting the reference sheet and messing with things outside of Eclipse. You have to generate that certificate and store it properly and point to it and all this wonderful stuff. On the other hand, building a receiver, so just the client side, is very easy. If you don't have to deal with the certificate stuff, totally business as usual. It's only the server's end that is complicated. The client's end, you can basically drop these in wherever you have a TCP socket, and it will just work from there. So if you want to just test it out from the client's end, that's very easy to do. So if you want to do some extra steps on the client's end, that is not rely on the system default, I've got a link that you can click for a list of all the different ciphers that are available in Java. This is how you specify them as an array of strings. Again, a minutia, weirdness, very strange. You can also, again, just get the user ciphers from their system, so just check their get supported ciphers that way, but this is not recommended because you're putting the burden on them. Then you also have to pick which protocol versions of TLS you support. Again, these all go in the client hello. So you've got your array of strings, your different TLS versions, and again, you could get supported protocols from your user system. Again, a bad idea. You could specify SSL v3 only and see what happens. What'll happen is everybody will deny your connection. And with this client, you could connect to services that have a valid TLS certificate and have their servers set up, and then we can read them. So there's a nice example in the book of making the client side only that you can use to connect to different websites and read their content from that application. So check that out if you're interested. And that's all the time we have for today. I'm going to upload an assignment later today, so be on the lookout for that. Otherwise, I will see you Monday for our last week before Thanksgiving.